So, I would like to continue our discussion of operational amplifiers. We don't have too much further to get through with them. We might even finish this within the next half hour. So, one piece of information which you may find useful and relevant, if you downloaded the slides from Avenue, I made modifications to the slides this afternoon, so you'll want to re-download the new version. Basically, I cut out like the second half of this set of slides, which was on the subject of filters, which addresses them somewhat more mathematically, but we have CEAB requirements that we need to get to after this, and maybe if we have enough time after that, we'll come back to the material on filters. But yeah, this thing on. Mic seems maybe it just needs the batteries replaced or something. But, anyway, so last time we did a couple of different circuit analyses. We did the differential amplifier circuit analysis, and we had just talked a little bit about the common mode rejection ratio. So just let's take it from here. So recall last time when we were talking about operational amplifiers, if you take the two input lines of an operational amplifier and you tie them to a common source, i.e. put it in common mode, you'll get a certain amount of gain produced that throws off the calculation with respect to the gain that you would expect. It's kind of gain that's always there, as opposed to gain which is proportional to the inputs. So one metric of note with respect to operational amplifiers is the common mode rejection ratio. This is how much of the common mode, what is the proportion of the common mode gain as opposed to the regular and normal gain of the amplifier. This is measured in decibels, right? So for an ideal operational amplifier, the gain of common mode would be equal to 0, and the common mode rejection ratio would be infinite because all of the common mode is being rejected. The larger the CMRR is, the more closely the op-amp matches the ideal behavior. This is kind of a thing that we've been doing with operational amplifiers this whole time. We make certain assumptions about how they operate, so to speak, and then we understand that those are approximations of the real behavior and not actually the real behavior. There are other factors involved, right? This is one of those factors. So, if, for example, we had the LM741 operational amplifier, if you look in its data sheet, the common mode rejection ratio is 90 decibels. The open loop gain K is typically around 200 volts per millivolt. So, if we take the gain as being 200 times 10 to the 3, and we plug K in here, right, we can calculate out what the common mode gain is, right? And it turns out to be about 32,000. So, therefore, if we had a voltage at the negative terminal of 2.4995 and a voltage at the positive terminal of 2.5005, that is to say, a difference between the two of these of 0.001, the common mode voltage would be 2.5 volts, right? So if we were to calculate then the common mode voltage multiplied by the gain divided by the rejection ratio, that would give us the amount of that the amount of the amplified voltage that would be due to the common mode. So there. Anyway, I'm not going to quiz you on this, so don't worry about it. So basic instrumentation amplification setup. Who here knows what this symbol means? What's it mean?
Variable resistor.
It is a variable resistance resistor, yes. This can be the symbol used for a potentiometer, because a potentiometer is a variable resistance resistor. But, you know, so we've got 3 operational amplifiers in this particular circuit. 2 resistors, R1, both having value R1. A resistor of variable resistance in the middle, R2. And then R3, R3, R4, R4 plus delta R4. We're going to assume that delta R4 is actually equal to 0. It's in there to be able to adjust the amplification, but we're going to hold it constant for the purposes of our analysis. At any rate, let's see if we can calculate VO in terms of all these, shall we? This will be, I promise, the final example of operational amplifier analysis that we do. So, just to remind ourselves, R1, R2, our circuit. So, before we start analyzing the circuit, or the first step to analyzing the circuit, we should be deciding what voltages are of interest here, right? So, even before that though, we should recognize that everything on this side of the dotted line is just the differential amplifier that we've already analyzed. So, if we consider two of the voltages that we're interested in as being the voltage here and the voltage there, let's call these points A and B, we can use the equation which we have already derived for differential amplifiers to relate VO to voltages A and B. Once we have done that, if we can find some way of relating VI1 and VI2 to voltages A and B, then Bob's your uncle. All right? Which is a very British way of saying we have completed the problem successfully. Good. So, bringing back our differential amplifier equation, V out is equal to the resistance of the feedback resistor over the resistance of the non-feedback resistor multiplied by VB, in this case, minus VA. Now, pulling in our previous example, this was RF and this was R, right? So, R4, R3. Good. So far, so good. So, in order to calculate voltages A and B, which are essentially the voltages which are coming out of both of these operational amplifiers, there are going to be two other points of interest, shall we say. Fortunately, due to op-amp laws, they're kind of like non-variables. But let's identify point 1 and point 2 as well. We will notice, hopefully relatively immediately, that op-amp law voltage, the voltages at both of the input leads are held to be the same. So, we can say, with confidence, VI1 is equal to V1 and VI2 is equal to V2. So we know the voltages across the resistor R2. We can therefore derive from Ohm's law IR2, well, you know what, I'm going to do this in a slightly more organized fashion. It's easier if I do it in sequence rather than just scrawling equations across the board randomly, right? You don't have to answer that. So, via Ohm's law, the current through the resistor I2 is equal to V2 minus V1 over R2. Ohm's law. Boom. So, now we pull in the operational amplifier law of current. How much current flows into the inputs of an operational amplifier in an ideal case?
0.
0! Yes, thank you. 0 the hero. So, we may therefore conclude that whatever current that's passing through R2 has nowhere to go except through either R1 resistor. I see I made it. There we go. Right? So, the voltage difference between A and B, we can use Ohm's law to get to that voltage difference, right? Via Ohm's law, VB minus VA is equal to the current through R2 multiplied by R2 plus 2R1. Because those are just resistors in series. Boom. So, having this and having that, we can actually now just perform the substitution. So VB minus VA is equal to V2 minus V1 times, well, over R2, pardon me, times R2 plus 2R1. There we go. No, that's not one of the ones that moves. Okay. Note our earlier equation. VB minus VA. We have that as a term of multiplication in the equation. So, we now, having an expression for it, can substitute it directly into the equation for V out. V out is equal to R4 over R3 multiplied by R2 plus 2R1 over R2 multiplied by V2 minus V1. And I might as well put the i's in there because, you know, makes it match up with the diagram. So from here, that's it. All I do is, you know, if you want to, you can write it slightly more nicely. Boom. So that one wasn't too bad, right? That's pretty good, right? Yeah. Did everybody follow that? That one was like, it didn't require nodal analysis. Well, maybe a little bit of nodal analysis, but you know, it was good. I liked that one. It was nice. Question.
What would happen if R2 is 0?
What would happen if R2 was 0? You'd have a short. Yeah. Right? If R2 was 0, then if there was any potential between the two input leads, like, I don't know, like that, I feel like that's an edge case where the op-amp would do something strange, you know? I can't verify that. You'd actually have to like wire the circuit up and try to blow up the op-amps to see if it would work, but you know. I don't know. I don't know what the op-amps would do in a situation like that. I know that it violates our ideal op-amp laws, but our ideal op-amp laws are like also ideal laws, so it's possible that one of the factors that we're ignoring might come in to save the day, but you know, I wouldn't bet on it, basically. So don't make that resistor 0. That's the long and the short of it. So, this is a slide that did the derivation. So we're talking about differential amplifiers, and it might be useful to describe why we might want differential amplifiers. You know, given that they measure, well, you know, there's sort of the obvious case where you need to measure or amplify the difference between the two voltage signals, right? But there's also, like, technically speaking, when you've connected one of the leads to ground, you're also measuring the difference between two voltage signals. Because ground, of course, is just a reference point, right? Like, if you have a voltage source, right? If you connect this down here, right? Or, let's not short it, right? If you connect ground here, we consider this to be like the 0 volt level and this to be the 5 volt level, right? But if you connected the ground up here, which, you know, not recommended, but you could, then you would have the 0 volt level here and the negative 5 volt level here, right? Voltage is a measurement of potential energy. And that potential is always relative to a reference point. It's like Gravitational potential energy. You guys remember gravitational potential energy from high school? Yep. Always relative to a reference point. In this room, this is the reference point. Voltage is the same way. Right? Good. So it turns out that it matters how things are grounded. It turns out that in actual physical reality, what two things considered to be ground might not actually be ground relative to each other, right? So if you have an instrument over here and an instrument over there, and both are connected to a ground, right? It depends on what connected to ground means. The most obvious case, let's imagine, right, that these two devices are, say, inside of different houses, right? So these two houses have two different grounding plates, right? What happens if there's, and let's imagine that they're like communicating with each other, right? What happens if these ground plates have a potential across them, right? Due to like soil acidity or something, right? What one person thinks is ground is not ground to the other, right? Now it turns out that you can actually have frequencies and signals pass through ground. So this is what's called ground loop interference or ground loop noise, right? So, yeah. Basically, the short way of finishing this and saying, okay, we're done, is don't connect to ground twice, because you'll set up a ground loop, and that could be a problem. So if you're designing devices that are connecting multiply to ground, try not to. Like, for example, when you hook up when you hook up a sensor, the ground lead comes along the data line, inside the data cable, you'll have both the power and the ground, right? Ever wonder why that is? Ever wonder why the device doesn't just use itself as ground or its own ground when it's doing that type of communication? Right? It's because of ground loop interference. These things could be connected to two different things that have a potential difference across them. So the grounds do not agree on what 0 volts is. Right? So that can lead to electrical interference. It can lead to problems. It might even be damaging to your system if it gets out of hand, because sensitive electronics be sensitive. But anyway, so we have a fundamental distinction between grounded and ungrounded sources, right? So if I take this very simple diagram, if it's just like that, ungrounded, obviously. If you put a ground on it, it becomes grounded. This is, yeah. Sorry, I didn't mean that to sound as patronizing as it came out. It's just that's where the logic led me. Obviously, all of you could have figured out that an ungrounded thing means that the ground isn't attached. But, this is my life now. This is teaching for me. I can't assume anything. But anyway. So there are lots of different devices that you have already encountered that are floating devices that aren't directly connected to ground. Multimeters, for example, batteries, thermocouples, transformers, and isolation amplifiers. None of these are ground connected. So these items can be referenced to ground by connecting one terminal to ground and using the other as input. It is then a grounded reference point. So your multimeter is floating until you connect it to ground, then it's grounded, obviously. So, if it's not grounded, then we need to measure the difference between the two terminals. That is, we need to use a double-ended or differential input. Double-ended differential sensing uses two analog input leads. The differential sensor, or the differential amplifier that we already discussed, that was in the instrument circuit, that is what we're talking about here, right? So, we do this to eliminate ground loop noise, right? If it's floating, then it'll be referenced to whatever the ground is for the thing that it's connected to. Obviously, it's not good to leave it floating, but if the intention is to leave it like, have it connected to something. Anyway, do you have a question? No? Okay. Just feeling your head? Okay. So ground loops then. If you have, say, some sensor, which is generating some voltage, right, and has some impedance, it's being read by an amplifier, or being amplified by an amplifier. If we have a common lead here between the two ground points, right, any potential difference between the two of these is going to cause a current running through these. And that doesn't have to be a large one, right? If there's anything that you should have picked up from our discussion of operational amplifiers so far, it's very small voltages matter with these things, right? Therefore, very small currents matter with these things. Like, if the amplifier is sensitive on the level of like thousandths of a millivolt, these types of effects can become quite pronounced. This is another reason why we use open or closed loop control rather than open loop control. So, this, which some might consider to be an obvious way of configuring a sensor and then a measurement system, contains a ground loop, right? Point, both connected to ground. There are several ways to break the ground loop. And that's basically the only thing that you can do with these things, is you have to break the loop, right? This is apparently a problem with like electric guitars and electric guitar amplifiers. So, like, think of an electric guitar as generating an analog electrical signal, because that's what it does, right? Everybody knows, who's tried an electric guitar, you have to run that thing into an amplifier, right? And then you have to run it to a speaker. Or sometimes you can get the speaker in the amplifier, but they're different things. So, if the two of them are connected to different grounds, then you'll get like a buzzing, humming noise in your speaker. That's ground loop noise, right? So, this should help you avoid electric guitar problems. So, one way that you can do this is you can put some resistance in the way of it, right? It's like it's almost like a pull-down resistor. So, configuration on the right uses AI sense to input to break the loop. So, this breaks the loop here, right? Notice that these guys are floating except for this one point in the middle. As you can see, there are several ways of going about it, both for differential, single-ended ground referenced, and single-ended non-referenced. Let's see, how many more slides do we have? 1, 2? Okay. Single-ended reference mode when input signal is a high level greater than 1 volt. Non-referenced single-ended mode when it's greater than 1 volt and the signals are less than 10 feet apart and the input signal is referenced to ground. Reference to ground, use non-referenced single-ended mode. Input is signal is floating, use reference single-ended mode. And that's it. All right, take her easy, folks.